Hi everyone, welcome back. Today we're doing lowest common ancestor of a binary tree. In the previous video, which we will also link in the description, we tried out lowest common ancestor of a binary search tree. In that question, fortunately for us back then, we could take advantage of the properties of binary search trees, and this allowed us to avoid the need for using depth search or breadth search to solve that question. So to be specific, back then, we could take advantage that all nodes that are smaller than the parent is on the left and all nodes that are larger than the parent is on the right. So by any chance, if P and Q are smaller, both smaller than the parent, then a lower common ancestor would be the left child of the current parent. So we could just iterate downwards and use a pointer to keep track of the current root. And if that's the condition, we would just traverse towards the left side of the subtree and set that next node as the lower common ancestor of that binary search tree. Unfortunately for this question, we're dealing with a binary tree this time, so we do not have that property to take advantage of anymore. So anyway, let's get started. For this question, we're given a binary tree and we have to find the lowest common ancestor of two given nodes in a tree. And according to the definition of lowest common ancestor on Wikipedia, the lowest common ancestor is defined as two nodes, P and Q, as the lowest node in T that has both P and Q as descendants, where we allow a node to be a descendant of itself. So for the first example over here, we're given a binary tree containing 351, 6200, now 74, now. So in this case, P equals to 5 and Q equals to 1 have the lowest common ancestor of 3. So in this case, 3 contains both 5 and 1 in itself and in its subtrees. So in this case, 3 is the lowest common ancestor. For the second example, now P is 5 and Q is 4. So in this case, the lowest common ancestor is 5 because 5 at its level contains P and in its subtrees it contains Q. So in this case, the lowest common ancestor is 5. And for the final example, if you have a binary tree that contains 1 and 2 and the tree is pretty much only containing P and Q, then the lowest common ancestor is the root of that binary tree. So in this case, the number of nodes in the tree is in the range 2 to 10 to the power of 5, which makes sense because the binary tree must at least contain P and Q. And for every single item inside this binary tree, their values range from negative 10 to the power of 9 to 10 to the power of 9. And all node values are unique. We do not have to worry about a situation where a parent's value is equals to its right or its left child. P will not be equals to Q. They are both unique, distinct tree node objects, and P and Q will exist in the tree. So to solve this question, we can do a variant of DFS, and it will involve some form of backtracking. So in this case, specifically, our DFS will return a boolean, and that boolean will indicate whether if that current node is containing P or Q. And before it returns that value, it will also check itself by any chance whether if itself, its left child or its right child contains P and Q. So if a certain node contains both P and Q, then this DFS will edit a global variable that indicates the lowest common ancestor. So once the lowest common ancestor is found, all subsequent calls of DFS will terminate prematurely because we have already found our lowest common ancestor. So with that was quite a mouthful. With that, let's get started. So the first step will be to define the lowest common ancestor global variable. This will keep track of the lowest common ancestor and whether if we have found it. So this will be of type optional of tree node, and this will be set to none. Next, we will define the depth search, and in this case, this will take in a given root. So let's call this root, and this will be tree node, and this will return back a boolean for whether if the current root over here contains P or Q. So let's do non-local lowest common ancestor so that this nested function has access to this variable that is outside of the DFS function. So once we're done, the first step is to check whether if the current root contains P or Q. So let's call this as middle, and this will be equals to root equals to P or root equals to Q. So as you notice, I'm doing direct object comparison. That's because both P and Q are guaranteed to be inside the binary search tree, like carbon copies with the same object, as the same object. So in this case, we can use double equality to compare two objects together. So the next step will be to do the DFS on root.left if root.left. So let's call this left, and this left indicates whether if P or Q is in the left subtree. So if root.left exists, else we will default this to false. So if you're curious, if you could just call DFS directly and just add an additional guard for whether if not root, return false, we could do that, but this is deliberate. We are deliberately avoiding that so that we avoid function calls on the call stack. Like, it's going to take some computation to keep track of the variables memory used in each function invocation. In short, we should avoid calling DFS if we can help it. So this is our way to do that. We will only call DFS if the left child exists. So at this point, before we check the right subtree, it would be nice to just do a sanity check whether if P and Q already exist in this current node and on the left subtree. And this allows us to avoid a DFS towards the right if the answer was already found. So we will do left, if left plus mid is equals to 2, then we would set the lowest common ancestor to the current root. It means that we have already found the current root as the lowest common ancestor. And we return false. And frankly, once you find the lowest common ancestor, this result here is no longer valid. Like this, I mean, it's no longer useful. This value will only be useful if by any chance the lowest common ancestor is above this current node over here. So if at line 22, this condition is not true, and what this means is that we have not found both P and Q, then unfortunately we would have to do the DFS to check whether if P or Q exists over there. So root.right if root.right, else false. And finally, now that we have traversed both the left and right subtrees of this current node, then we can check whether if left plus mid plus right is equals to 2. In other words, if we have found both P and Q in both left, right, and current node, then we can set the lowest common multiple similarly to root and return false. And if we still haven't terminated and return false at this point, then what this means is that we would just return left or mid or right. At this point, only one of these booleans over here will be true, or all of them might just be true. So, I mean, all of them might just be false. So this evaluation over here would just be 0 or 1. There's also one final optimization that we can do. If lowest common ancestor is already found, then we can return false. And this will save us the need to do a left DFS on the left side if we have already found our answer. So that's pretty much it for this approach. Let's call DFS on the root, and let's return the lowest common ancestor. After this DFS over here, the lowest common ancestor will be set to the right answer, and we will just return that answer. So let's try it out with one test case together. So let's use this example 1 as the test case. So now lowest common ancestor will be none, and we will start the DFS over here. Let's keep track of a call stack as usual. And this call stack will be calling DFS on tree node equals to 3 over here. And P, I guess, yeah, that's not necessary. It's just DFS. So at this stage, lowest common ancestor is still none. So we will skip this check. Middle in this case is 3. And we're looking for P equals to 5 and Q equals to 1. So in this case, mid is not equals to either, so mid is equals to 0. Left in this case will be root.left exists, tree has a left child, so in this case we will perform DFS on root.left. So let's keep track of that, root.left. This is just to let us know that we are currently doing the root.left over here. And let's create a new function invocation and call this tree node 5. So we are evaluating this. So now we're at tree node 5. This is going to be ignored because our lowest common ancestor is still none. I'm sorry for mixing that up. But in this case, mid will be true in this case because 5 is indeed equals to p. So this will be set to 1. And left in this case, we will do a DFS on 5 on root.left. So we will make another function invocation on DFS tree node 6. So in this case, 6, we will ignore this as usual because we have not found the lowest common ancestor. 6 mid will be equals to 0. Actually, I should put this as mid equals to 1. Yeah, just so that it's easier. So 6 mid is equals to 0. Left will not be evaluated because 6 doesn't have a left child. And in this case, this is just left equals to 0. Actually false, yeah, and this is true. Yeah, this is more accurate. So left plus mid in this case will be sorry, we're evaluating for 6, right? So this is false. Sorry for the confusion. But in this case, for 6, it will be false plus false. So this is 0. So this will evaluate to 0. So this will be ignored. Now we will check right. Right doesn't have any children, so right will be equals to false. And in this case, left plus mid plus right is just false plus false plus false equals to 2. And this will evaluate to 0. So line 36 to line 38 for tree node 2 would also be ignored. So we will return left or mid or right, false or false. Okay, so in this case, in short, we return false from tree node 6 back to 5. So in this case, left is equals to false. So we will pop this off the call stack because we evaluated it, and we will continue. So now we end off here, and we just receive back false from receive false back from tree node 6, and we are back at evaluating tree node 5. So left plus mid in this case would be false plus true. So this is 1 equals to 2, so this is false. Lowest common ancestor, yep, we will skip all of this stuff. Right in this case is 2. So, but in summary, I'm just going to skip some steps here, but you can see that there is no P or Q on this side over here. So let's just set this to false and skip all the function calls that we might have made. So in this case, this would be false plus true plus false. So this will evaluate to 1 equals to 2. So this will be false, so we will skip that. And in this case, we will return false or true or false. And this will evaluate to true. And we will pass control from 5 back to 3. And in this case, mid is equals to false, left is equals to true. And you get the gist of it. But in summary, if we skip some steps, we will evaluate that right is equals to true. And this will evaluate to left plus mid plus right equals to 2. And we will set the lowest common ancestor to the current value, which is 3, giving us the answer 3. So this looks great. Let's run this against some test cases. And let's submit this. So as you can see, sometimes we can't always afford to trace out the whole stack call of a certain test case, but it's okay as long as we are convinced that the logic behind the implementation makes sense. So I hope this was a pretty clear demonstration of tracing. So in summary, the time complexity, if we define n to be the number of nodes and b to be the depth of the binary tree, then in this case, the time complexity will be O(n) because we perform a depth first search across the whole tree. So for the space complexity, in this case, because we use a recursive implementation, it's going to be OD. But in the case of a binary tree that is imbalanced, D will be equals to N, and space complexity will be ON. So in summary, I personally find that the hardest part of this question is figuring out the DFS condition. So fortunately, with enough practice, we will get used to such questions. So I hope that this was a good demonstration of depth first search, and this involves some form of backtracking where every single node would backtrack and pass back a boolean that indicates whether P or Q exists back to the parent. So this is pretty much DFS with backtracking. So that's pretty much it for this question. I hope you liked it. If you like it, please give us a like and subscribe, and we will see you in the next video.